Moving on to 18.3, structure and general properties of the metalloids. Here we're going to describe the general preparation, properties, and uses of the metalloids, and then describe the preparation, properties, and compounds of boron and silicon. So there are 6 metalloids: boron, silicon, germanium, arsenic, antimony, and tellurium. They look like metals, but they don't conduct electricity as well as metals, so they're called semiconductors. And this is because the electrons are more tightly bound to the nucleus than other metallic conductors. Their chemical behavior is in between that of metals and nonmetals. So they can form covalent crystals, and they generally don't form monatomic anions. So you don't find generally like a boron -3. Boron is somewhat similar to both carbon and silicon, except it has one less valence electron than it has valence orbitals. So because of that, when it's in most compounds, it has an oxidation state of +3. But because of this electron deficiency in it, it can form other oxidation states that are sometimes fractional. So it's kind of cool, and it can act as a Lewis acid. Boron tends to form 3 bonds and with an sp2 hybridization. Silicon tends to form tetrahedral structures that have an sp3 hybridization, and then it has a formal oxidation state of +4 and can act as a Lewis acid. Now, arsenic and antimony can form compounds that have oxidation states of 3+ or 5+, but arsenic can also form what are called arsenides that have an oxidation state of 3- as well. So arsenic's a little different. Tellurium is very reactive and can combine with most elements. It can make tellurides, where it is tellurium 2- when it bonds with active metals and lanthanides. It also can have an oxidation state of 2+, or that should be a 4+. Sorry, not 4 blank. When it combines with oxygen, fluorine, or chlorine. So when it comes to their structures, covalent bonding is really the key to their crystal structures. Silicon, germanium, arsenic, antimony, and tellurium are lustrous and metallic looking, and silicon and germanium also have a diamond structure. So in this structure, their structures, the atoms are covalently bonding to 4 neighboring atoms at the corners of a tetrahedron. And silicon and germanium, the crystals they form are basically one giant 3D molecule. Arsenic has quite a few allotropes, where the most stable is kind of layered-like, where you have these puckered sheets of atoms. So in each atom is bonded to 3 other atoms. Antimony is very similar to arsenic, and both arsenic and antimony have similar structures to graphite. Tellurium can form crystals that have infinite spiral chains of atoms, so each atom is bonded to 2 other atoms. And now we have boron, which is a little different. When it is crystalline, it's transparent, and it forms an icosahedra shape with a boron atom at each corner of the icosahedron. It has kind of a similar packing to the cubic closest packing of spheres. If you remember when we talked about packing of spheres, I think that's towards the end of Chem 1A. Or 2A, sorry. And then there's different arrangements and connections depending on the actual form of the boron itself. And then just a little fun fact, silicon gets its name from the Latin word for flint, silex. I don't know if I pronounced that wrong or not, and Jeff isn't right next to me to tell me. And it can form compounds that have, goes silicon, oxygen, silicon bond, so SiO-Si, which is a very important for minerals. So in the mineral world, that is very important, whereas on the other hand, carbon forms carbon-carbon bonds, which we need for the plant-animal worlds. So here is some pictures of some of these structures. Arsenic is an A, so you can see kind of those puckered sheets with the shape. And antimony is kind of similar, so they have these layered sheets that are just kind of attracted to each other, but they're not actually bonded together. And then graphite is in C, so you can kind of see the similarities, except graphite isn't puckered, it's planar. And then tellurium has these spiral chains that you can see in D. And here's an icosahedron for boron. So this is symmetrical with 20 faces on it, with each face being an equilateral triangle, and the faces meet at 12 corners. So you can see all the borons at every single corner. Wherever my fellow nerds are, makes me think of a 20-sided die, and I want to go play some D&D. So let's go ahead and start talking about boron. Boron constitutes less than 0.001% by weight of the Earth's crust, and it occurs naturally in compounds with oxygen, such as boric acid and borax. Elemental boron is basically chemically inert at room temperature and will only react with fluorine and oxygen at room temperature, which will form boron trifluoride and diboron trioxide. It will react with all nonmetals at higher temperatures. So you heat it, then it'll react with those nonmetals, except of course noble gases, and it will react with most metals. If you heat elemental boron with concentrated nitric or sulfuric acid, which are oxidizing acids, it will oxidize to B2O3. It will not react though with non-oxidizing acids. So if you add it to hydrochloric acid, nothing will happen. Most of the boron compounds themselves will react with water to form boric acid, which is this BOH3. If you reduce boric acid with magnesium powder, you end up forming this amorphous powder of boron. And it looks to be an amorphous solid means it looks to be a solid, but there's no long-range order to it of the atoms in it. And then you can also take impure boron, make it into boron trichloride, and then react it with hydrogen and heat. So we can take, this is another way of writing boric acid, B2O3. Or no, this isn't boric acid, this is the oxidized boron. And we can react it with magnesium. And this is what gives us this amorphous boron and magnesium oxide. And then we can also take boron trichloride, which is a gas, react it with hydrogen gas, and give it a ton of heat at 1500 degrees Celsius, and we get boron and hydrochloric acid. And now silicon, interestingly enough, makes up 1/4 the mass of the Earth's crust, second only to oxygen. And it's going to occur in compounds where silicon atoms tend to be at the center of a silicon-oxygen tetrahedron. The different compounds with silicon in them have a bunch of different connectivities. It could be in chains and layers and 3D frameworks. Not the bulk of rocks, it's the bulk, and there's supposed to be E in frameworks, but it tends to make up the bulk of rocks, soils, clays, ceramics, and glasses. So silicon is all over the place. We can make it by reducing silicon dioxide at high temperatures with a strong reducing agent like carbon or magnesium. So we can take our silicon dioxide, which is sand, give it some carbon, and some heat, and we get silicon and carbon monoxide. We can also do this instead with magnesium, and we get silicon, but this time we get magnesium oxide. So pure silicon is very important for semiconductors. When it's impure, we can convert it into silicon tetrahalides and then decompose it at high temperatures and then purify it. Passivation actually does occur for silicon. So remember that there's that coating on the outside, and it generally occurs as silicon dioxide, which you can remove by throwing it into a hot aqueous base. Okay, so when you do that, you take... Ah, my book! No! Sorry, I dropped my book, which has my notes in it. Silicon, silicon. There it is. Okay, like I was saying, with our passivation, we take some silicon and some hydroxide. And this will give us this SiO4 4- and hydrogen gas. Again, it'll also react with halogens to make these volatile tetrahalides, such as silicon trifluoride. Should be a lowercase, and it does not actually form double or triple bonds very easily. It's generally going to form SiX4 compounds, where X means a halide, so SiF4, SiCl4, and then it can act as Lewis acids to form 6-coordinate silicon instead of forming double and triple bonds. And then just a quick little blurb on antimony. It reacts pretty easily with halogens to give us trihalides. And then if you add excess fluorine and chlorine, it can form pentahalides. And depending on the stoichiometry, you can get antimony 3 sulfide or antimony 4 sulfide as well when you heat it with sulfur. And antimony is more metallic like than arsenic because it is lower on the periodic table. So this is a zone refining apparatus for purifying silicon. Take the impure stuff, and then you get the molten, and the pure silicon is able to come out. So now we're going to talk about boron and silicon halides. We can get boron trihalides prepared by direct reaction of the elements. So literally you can take boron, react it with chlorine, and you get BCl3, for instance. And these are going to be nonpolar sp2 hybridized molecules with a trigonal planar molecular geometry. When you have the boron trifluoride and boron trichloride, these are colorless gases, but boron tribromide is a liquid, and boron triiodide is a white crystalline solid. You can also take your trihalides and add them to water to give us boric acid, and then your hydrohalic acid. So except for trifluoride, so if we take BCl3, for instance, and add it to water, we get boric acid, BOH3, and hydrochloric acid. Now, boron trifluoride does not undergo this reaction. However, you can react it with hydrofluoric acid to get fluoroboric acid. So we take BF3 and hydrofluoric acid, HF, and water. And we get H3O plus and BF4 minus, so which comes to be HBF4. Now, when it comes to silicon tetrahalides, they've all been prepared. The silicon tetrachloride, we can make by direct chlorination at high temperatures, or we can also take silicon dioxide and heat it with chlorine and carbon, which tends to be a little bit more popular. So we take SiO2 solid, give it some carbon and chlorine gas, and heat, and we get SiCl4 gas and CO2 gas. And so the silicon tetrachloride is a covalent tetrahedral molecule. It's nonpolar, has a lower boiling point, and is a colorless liquid. You can also prepare it by reacting with hydrofluoric acid. So we can take our silicon dioxide also and react it with hydrofluoric acid, HF. And this will give us silicon. Oh, that should be tetrafluoride, not tetrachloride. Sorry. So that gives us SiF4 plus 2 waters. And then one thing that's interesting is hydrofluoric acid is the only common acid that will actually react with silicon dioxide or with silicates. That's because the silicon-fluorine bond is the only bond that silicon forms that is stronger than silicon and oxygen bond. And this is why you cannot store hydrofluoric acid in glass bottles. So most acids and a lot of compounds are stored in glass bottles, and these tend to be borosilicate glass, boron and silicon. And because you have silicon in there, the hydrofluoric acid can react with it and form those SF bonds. So hydrofluoric acid has to be stored in very specialized bottles. Usually it's a type of plastic that it will not react with. Hydrofluoric acid is really weird stuff because it's considered a weak acid, but it's still very, very dangerous and reactive. So this is showing us the BF3 molecule acting as a Lewis acid. So it's accepting a pair of electrons from a fluoride ion. So a little bit about their oxides and derivatives. Boron burns at 700 degrees Celsius in oxygen, and this forms boric acid, B2O3. So this is another way of writing the formula of boric acid. Where was I? And it's another form of boric acid, or boric oxide, not boric acid. I was like, wait. So burn in oxygen, you make boric oxide, which we can use to make borosilicate glass. Boric oxide is going to dissolve in hot water to form boric acid. And then the boron in this should be up here, is sp2 hybridized, and it's at the center of an equilateral triangle that has oxygen at the center. So you've got boron, and then these oxygens at the corners in this equilateral triangle. sp2 hybridized means it's 2D, basically, it's flat. It is a very, very weak acid, and it can only act as a Lewis acid. If you take boric acid and heat it to 100 degrees Celsius, you make metaboric acid, which, I'm sorry, that is my new band name, so don't steal it from me. When we hit 150 degrees, the boron-oxygen-boron linkages form, and this actually creates tetraboric acid, H2B4O7. And then if you keep heating it, you end up taking out the water, and we return to boric oxide. So yeah, boric acid I think is pretty darn cool. If we do, to use boric acid as a Lewis acid, so we have BOH3 and water. We get a nice equilibrium where we make BOH4 minus and H3O plus. So this is how boron, this boric acid can act as a Lewis acid. Here's some lab glassware like Pyrex or Chemex, or some of the big Pyrex and Chemex are some of the big brands. You probably actually have some Pyrex glass in your kitchen, and maybe a measuring cup. It's borosilicate glass. It does not break when heated, which is why it's so good. The borates in the glass help keep it from thermally expanding and contracting too much, which is what can lead to cracks. from thermal shock. And this is showing you the planar structure of boric acid from the three OH groups that are at 120 degrees from each other in this equilateral triangle. And now we have borates, and these are salts of boron oxyacids. We get them from reacting base with an oxyacid or by fusing boric acid or boric oxide with a metal oxide or a metal hydroxide. We can get these anions that are trigonal planar as BO33-, or we can get complex chains that have 3 or 4 coordinated boron atoms. One example, the most commercially important borate is borax, and it is used in a lot of laundry detergent. I believe it's also used to kill bugs. It's, if I remember right, it's like sweet, and it basically it's like used for killing ants. They take it to their colony and it slowly kills them over time as they eat it. Some type of boron compound. I think it's borax, but I can't say for sure. So you can see these borate anions. In A you have CaB2O4 and it's showing you the B2O4 2- unit. In B you have KB5O8 tetrahydrate, and then C Na2B4O7. Let's see, with 10 waters. I always forget what the 10 is. And then the anion in CaB2O4 is an infinite chain, so it's kind of a polymer. It just keeps going and going and going. So these are some cool structures. Boron really is cool, really, really cool. So the chemistry. For those of you that are chemistry majors, when you transfer and you go on to inorganic chemistry and you get into the advanced stuff, you'll spend a bit of time on boron chemistry, and it really is fascinating. So now we're going to start talking about some boron and silicon oxides and derivatives, starting with some silicon ones. Silicon dioxide, aka silica, comes in both a crystalline and an amorphous form. The crystalline form of it is quartz, which is used in architecture, decor, jewelry, as well as frequency control and radio transmitters. So there's some quartz crystal right there for you. It has a bunch of polymorphs or crystalline forms in nature. If you add some trace amounts of the iron 3 ion into the quartz, you get amethyst, and that beautiful purple color. Oh, excuse me. Interestingly enough, amorphous silica is used to make things like quartz tubing and lenses. So when you see something that has quartz lens or quartz tubing, it's made from the amorphous form of silica. And then opal is actually naturally occurring amorphous silica. So opal, amethyst, quartz, they are all forms of silicon dioxide or silica. Silicon dioxide has a very different structure than carbon dioxide, even though silicon is right underneath carbon on the periodic table. Silicon dioxide is a covalent network solid, so that means you have a bunch of linkages. So each silicon atom is linked to 4 oxygen atoms by single bonds, whereas carbon dioxide you have individual carbon bonded to 2 oxygen molecules. And what's kind of cool is quartz crystals themselves are actually macromolecules of silicon dioxide. So you're holding a quartz crystal and you're holding one big molecule. Group 14 atoms that are in and above the second period, above it in the second period, like carbon, can form strong pi bonds, but silicon really doesn't. Below the second period, these group 14 atoms don't readily form pi bonds, and if they do form, they tend to be pretty weak. Quartz itself melts around 1600 degrees Celsius to a viscous liquid, very, very thick. So you melt it and then it undergoes supercooling and it ends up forming silica glass. And this glass is a random arrangement of silicon tetraoxide tetrahedra. And what's interesting about it is it's transparent to both visible and UV light. So it's very, very important for in lamps and when you're in the optical instrument manufacturing. So a lot of times you'll have quartz cells where you put a sample in that passes light through it, and so because it's transparent, that quartz cell doesn't affect the sample itself, and you're able to look at how that liquid or solid or whatever you're looking at actually affects the bending of light, for instance. And then what's kind of cool is rapid temperature changes do not cause fracturing. So quartz is used in ceramic cookware like Corningware. So I got some here. I have a nice Corningware set at home, and I don't know if you guys know about this. I'm sure you do, but vintage Corningware has, like, people are trying to sell it for like $1,600 and stuff on eBay. It's kind of crazy. And then you can add small amounts of other compounds to the ceramics that to give it some other characteristics that might be useful for whatever type of ceramic you're using. So silicon dioxide is very, very useful. So this is showing you dry ice CO2 versus silicon dioxide. Carbon will form double and triple bonds to make discrete molecules, whereas silicon dioxide is an infinite network of oxygen atoms bridging between silicon atoms, and each silicon atom having 4 oxygen single bonds.